Have you ever stopped to think about how scientists measure something they literally can't see? Like how much salt is actually in that glass of salt water? It's kind of like a puzzle with invisible pieces. Well, today, we're going to crack that code. We're diving into the secret language and the powerful calculations chemists use to reveal the unseen. So here's our game plan. First, we'll tackle the big question that gets this all started. Then, we'll tech out a super precise technique called titration. After that, we've got to learn the language of concentration. And finally, we'll put it all together and do some real calculations. Let's get into it. You know, in the world of chemistry, it's one thing to know what's in a sample, but the real magic, the real power, comes from knowing exactly how much of it is in there. And that, right there, is the central challenge. Think about it. You have a completely clear solution. How in the world do you figure out its concentration without, tasting it, which you should never ever do? Chemists needed a way to get a number, a precise mathematical answer. This is where we make a really important distinction. You've got qualitative analysis, which just tells you what's there. It says, yep, there's vitamin C in this orange juice. But then you have quantitative analysis, and that's our focus today. This tells you how much. It says there are exactly 50 milligrams of vitamin C per 100 milliliters of juice. It's the science of how much, and it's absolutely crucial for, well, pretty much everything. So, how do we get those numbers? Well, one of the most classic and incredibly accurate methods in the chemist's toolkit is something called titration. This technique is a workhorse used everywhere from food science labs to pharmaceutical companies. At its core, titration is just a really, really controlled chemical reaction. The whole idea is to use a solution you know everything about to figure out a solution that's a total mystery. You just carefully add your known stuff to the unknown stuff until, boom, the reaction is perfectly finished. So in this process, we've got two main players. First, there's the analyte. That's our mystery liquid, the one we're trying to figure out. Then you have the titrant. This is our perfectly calibrated tool. We know its concentration down to the decimal point, and we're going to use it to measure our analyte. And the process itself is super methodical. You start with a very precise amount of your mystery analyte in a flask. You add a couple drops of an indicator. That's a special dye that changes color at just the right moment. Then from a long glass tube called a burette, you add the titrant, drop by drop by drop, until that color suddenly changes. That color change is your signal to stop. Okay, now this is a really subtle but super important detail. There's the equivalence point, which is the perfect theoretical moment when the molecules of the titrant and analyte have perfectly balanced each other out. The only problem? You can't see it. It's invisible. That's where the endpoint comes in. The endpoint is what you can see. It's that physical color change. The true art of a good titration is choosing an indicator where that visible endpoint happens at the exact same time as the invisible equivalence point. All right, so before we can start crunching the numbers from our titration, we need to learn how to speak the language. Chemistry has a very specific way of talking about how much stuff is somewhere, and it all revolves around one central idea. And that idea is the mole. Seriously, this is probably the most important number in all of chemistry. Just like a dozen means 12, or a pair means 2, a mole means 6.023 times 10 to the 23rd of something. It's a mind-bogglingly huge number, but it's just the way chemists count atoms and molecules in manageable chunks. It's their dozen. So how do we find out how many moles we're dealing with? We're not going to count them, obviously. We use this simple formula right here. You just take the weight of your sample in grams, and you divide it by its molecular weight, which is just a known value for how much 1 mole of that substance weighs. Easy enough, right? Now we can finally talk about concentration in a meaningful way. The most common unit is molarity, which we show with a capital M. And it's really simple. It's just the number of moles of your substance that are dissolved in exactly 1 liter of solution. So a 2-molar solution is twice as concentrated as a 1-molar solution. And of course, there's a formula for it. Molarity is just the moles of your stuff, your solute, divided by the total volume of the solution in liters. This formula is so powerful because it connects the invisible world of moles and molecules to something we can easily measure in the lab, like liters. Okay, we've got the theory, we know the language, now for the fun part. Let's actually put these formulas to work and crack some chemical codes. So here's our first problem. We've dissolved 4 grams of sodium hydroxide in 2 liters of water. The question is simple. What's the molarity of this solution? To solve this, we can actually get a little clever and combine the two formulas we just learned. Since molarity is moles per liter and moles are weight divided by molecular weight, we can just mash them together into this one handy formula. Molarity equals the weight divided by the molecular weight times the volume. Now we just plug in our numbers. Our weight is 4.0 grams. We're going to divide that by the molecular weight, which is 40 grams per mole, multiplied by our volume, which is 2 liters. All that's left is a little bit of arithmetic. And when you do the math, 4 divided by 80, you get 0.05 molar. And just like that, we've done it. We took a weight and a volume, and we figured out the exact molecular concentration of a solution we can't see into. Pretty cool. All right, let's try a different kind of problem, one that happens in labs every single day. Let's say you have a bottle of super concentrated sulfuric acid, and you need to make a much weaker, diluted version for an experiment. How much of that really strong stuff do you need? For this, there's an incredibly useful and elegant little equation. M1V1 equals M2V2. All it says is that the molarity times the volume of your starting solution, your concentrated stuff, is equal to the molarity times the volume of your final diluted solution. It works because when you add water, you're not changing the number of acid molecules. You're just giving them more room to swim around in. So let's plug in what we know. On the one side, our starting molarity, M1, is 17.45 m. The starting volume, V1, is what we're trying to find. On the 2 side, our final molarity, M2, is 0.1 m, and our final volume, V2, is 500 milliliters. You just do a little bit of algebra to solve for V1, and you get your answer. You need to measure out exactly 2.865 milliliters of that concentrated acid and then dilute it with water up to a final volume of 500 milliliters. That's how you get the perfect solution every time. So there you have it. With just a few key concepts and a couple of straightforward formulas, you now have the power to measure the invisible. You can quantify the world on a molecular level. So the next time you look at the nutritional information on a bottle or the active ingredients in medicine, you'll understand the language it's speaking. The only question left is, now that you know the code, what puzzles are you going to solve?